Alright, everyone, so welcome back as we wrap up week 3. So we're going to talk today about what are called implicit derivatives, and we'll see where that name comes from in a moment. So far we've come up with broadly 7 rules, in addition to kind of some special rules that we've had. So we've had our constant rule, we've had our sum and difference rules, our constant multiple rule, power rule, product rule, quotient rule, and chain rule, and then we also had some special rules, like we had um, the derivative rules for sine and cosine. We did also have that e to the kx rule, but really that one falls under the chain rule. Okay, so let's start with this. So the graphic is supposed to be a unit circle, but as you can see, the x-axis is longer than the y-axis, so the thing kind of looks like a football, but it's the unit circle, trust me. So we have a plot of the unit circle. The unit circle we can has the relation x squared plus y squared equals 1. So let's go and find the slope of the tangent line at 2 points. So 1/2 and square root of 3 over 2, and then also 1/2 minus square root of 3 over 2. So one question that we have is, how do we actually find dy by dx? And the reason why this is important is that we could see that the circle fails the vertical line test. So if we took a vertical line and we moved it across the x-axis, what we'd see is that there'd be 2 points on the unit circle. So suppose you have a vertical line here with the y-axis, you have a point at 1 and another point on the circle down at -1. So that's going to tell us that this relation x squared plus y squared equals 1 fails to be a function. Because a function, as you might recall from maybe high school algebra or something, you have to have exactly one output for every input. So if you proposed a function and you gave the input of 0, we'd have to be able to get 1 and also -1, so we're going to have problems there. Well, one easy way of solving this is to say, well, listen, if we take the top half and we take the bottom half, we'd get something that would pass the vertical line test, so we'd get functions out of that. Right, so the first thing that we could do is we could say we've got y1, which is square root of 1 minus x squared, so the top half of the circle, and then we've got a y2, which is minus square root of 1 minus x squared, which is the bottom half of our circle. So let's just go and find derivatives as we normally would based on these. So when we want to find the slope of the tangent line at 1/2 square root of 3 over 2, we're going to use the top half of the circle, so we'll use y1, and when we want to find the slope of the tangent line at 1/2 minus square root of 3 over 2, we'll use the bottom one, we'll use y2. Okay, so let's do that. We have a chain rule. We know how we can solve things with the chain rule, so our outer function here will be square root of x. Our inner function will be 1 minus x squared. We'd find that f prime is 1 over 2 square root of x, and g prime is minus 2x. So we'll have that y1 prime is minus x over square root of 1 minus x squared from our chain rule, f prime at g times g prime. And when we want to find the slope of the tangent line at 1/2, we'll just have this line here. So we'll have the line y equals y1 prime at 1/2 times x minus 1/2 plus y1 of 1/2, which we already said is square root of 3 over 2. And we'd find that that slope is going to be minus 1 over square root of 3, and that kind of makes sense, because if we look at the picture, we see the slope should be negative. So we'd wind up with a final line of y equals minus 1 over square root of 3x plus 2 over square root of 3. Just as a side note, I don't care if you have square roots in the denominator. Maybe from high school or whatever, you were told that you shouldn't. It's not that big of a concern. Okay, so then the second part. So we said, well, we could find the slope of the tangent line up here. How about down here at 1/2 and minus square root of 3 over 2? So if we do that, we're going to get something very similar. So y2 is minus y1. So y2 prime is minus y1 prime. So we'll just get x over square root of 1 minus x squared. And we'll do the same kind of construction. We'll take our tangent line equation, put in the various pieces. And here our y2 prime at 1/2 will be 1 over the square root of 3, and that'll give us altogether the tangent line y equals 1 over square root of 3x minus 2 over square root of 3. And again, that makes sense because we can see this tangent line here as positive slope. Okay, so that's one way of doing it, but maybe it's a little bit overkill, because what we had to do here was come up with two different functions and then go and find the derivative. Now in this case the functions were really easy to work with, but you could imagine this could be much worse. So maybe this seems a little bit like overkill. So what we did here was work with two functions that were kind of nicely related, so everything was pretty easy to work with. But you can imagine that we could look at something that doesn't pass the vertical line test, but it's much, much worse than the unit circle. So what we'd like to do is devise a different way of dealing with this. So what we're going to do is instead we're going to assume that y is a mystery function of x. So before we actually found explicit formulations for y, now we're just going to do is we're going to say it's some unknown function of x. We don't know what it is, we don't really care. And what we're going to do is we're going to take derivatives of both sides. So remember that what we do to one side, we have to do to the other. So on our right-hand side, we have the derivative with respect to x of 1. Well, that's just 0. And then on the left-hand side, we have a derivative with respect to x of x squared plus y of x squared. So again, y is a mystery function of x. Well, the derivative of x with x squared, that's just our power rule, so we'll get a 2x. But now we'll get a derivative with respect to x of y squared. Okay, so y squared, we can look at it as a function composition. So we can look at it as an outer function of x squared. So y squared we can look at as a function composition. So our outer function is going to be x squared, and our inner function is just going to be g of x equals y. So in this case, from our chain rule, we'll get f prime of g times g prime. G prime is just going to be dy by dx, or y prime again. I'm kind of mixing notation here, but it all means the same thing in the end. And f prime is clearly 2x. So our f prime of g will give us 2y, and our g prime will give us a dy by dx. And what we're trying to find here is this dy by dx. Okay, so what we wind up with, based on step 3, is we get a 2x plus a 2y times dy by dx, and we want to solve for dy by dx. When we solve for dy by dx, we'll put all of the terms that don't have dy by dx, in this case just 2x, over onto one side, and then we'll keep on, in this case the left side, all the terms that have dy by dx on them. And then solve for dy by dx. So we'll now just divide both sides by a 2y, and we'll get dy by dx is minus x over y. Okay, so dy by dx, solving it at x equals 1/2, y equals square root of 3 over 2, so that's just what this vertical bar means. It means we're going to evaluate at some point, or in this case, xy point. So we'll get minus x over y minus 1/2 divided by square root of 3 over 2 gives us minus 1 over square root of 3. And that's exactly what we found was the slope of the tangent line at this point 1/2 square root of 3 over 2 just a moment ago. So in this case, the benefit of this is that we only need to worry about the original relation that we have. We don't have to worry about coming up with a function. Instead, we just do this implicit derivative measure method. Okay, so what are the actual steps that we just did? So really all we did was 3 steps. Step 1, we have, we assume that y is a mystery function of x. So usually the simplest way to write it is just say, everywhere where you have a y, it's just y of x. We're not ever going to try and find a y of x. And in the 3 examples that we have here, you wouldn't want to try and find a y of x. Step 2, take the derivative of both sides with respect to x, and whenever we encounter a y of x, you must use the chain rule. Because y is assumed to be a function of x, if you just say that derivative is 0, that's not correct, because y is a function of x, so it changes as x changes. Okay, and then the third step, which is basically just a kind of high school algebra problem, is solve whatever you wind up with for dy by dx. So it's the exact same thing as if you were given in, I don't know, grade 10 or something. Solve this equation for w. That's all you have to do. So the hard part is really step 2. Okay, so one thing to note is that whenever we're trying to find the derivative with respect to x of some function of y of x, so f is x squared, for example, we'll get f prime of y of x times dy by dx. And whenever you do these, you'd better get dy by dx is falling out, because otherwise something kind of suspicious has happened. Okay, so the first example that we're going to do is we're going to find dy by dx for y sine of x equals x cubed plus cosine of y. Okay, so step 1, we assume that y is some mystery function of x, and then the second thing that we're going to do is take derivatives of both sides with respect to x. On the left-hand side, we have y of x times sine of x. So we have two functions of x multiplied together. That says we need to use our product rule. So first, we're going to get the derivative of y times our second function, so times sine of x. And then we're going to get y of x times the derivative of our second function. So here, that'll just give us a dy by dx times sine of x plus y times the derivative of sine, which is cosine. Okay, so that gives us our left-hand side. On our right-hand side, we have the derivative of x cubed, which is just 3x squared from our power rule, plus the derivative of cosine of y. So again, this is where we're going to need to make use of the chain rule. So cosine of y, or cosine of y of x, depending on how you want to write it, we'll write as a function composition. Our outer function f will be cosine. Our inner function g will be y. So usually whenever you do a chain rule with these kind of ones, the inner function is usually y. On occasion, if you have to do a chain rule twice, maybe it's some y of something simpler, but usually g is just y. Okay, so f prime is then minus sine, and g prime is dy by dx. So the derivative of x of cosine of y of x is our f prime of g times g prime, so minus sine of y times dy by dx. So when we combine our left and our right hand sides, we get dy by dx times sine of x plus y cosine of x equals 3x squared minus sine of y dy by dx. And now at this point, all we need to do, so we've done from this, we've done step 1 and we've done step 2. Now all we need to do is solve for dy by dx. So what we're asking here is just isolate this equation for the dy by dx. And what we're going to do is put all the terms that have dy by dx on one side, put the terms that don't have dy by dx on the other side, factor dy by dx out, and then isolate for it. Okay, so we'll go and put the terms that have dy by dx over on the left, and the terms that don't have dy by dx on the right. On the left-hand side, because both terms have dy by dx in them, we'll factor dy by dx out, and then we'll divide both sides in this case by the sine of x plus sine of y, and that'll tell us that dy by dx is 3x squared minus y cosine of x divided by sine of x plus sine of y. If you want to put in y of x's, that's totally fine. Mostly the reason why I drop the parentheses is to save space and maybe make it a little less cluttered. But if you want to leave them as y of x's throughout, that's fine. Just make sure the context is clear to at least you that sometimes you'll have y of x and it'll mean a function, but other times you could have an x meaning like a multiplication or something. So just make sure that's clear. Okay, so that tells us the process that we want to do. So 2 more examples. So let's find the equation of the tangent line to x squared plus xy plus 2y cubed equals 4 at the point minus 2, 1. Okay, so one thing we could do if we really wanted is we could just make sure that the point xy equals minus 2 and 1 is actually satisfied by this, is going to satisfy this relation. If we did, we'd have a minus 2 squared, which is 4, plus minus 2 times 1, so we have 4 minus 2, plus 2 times 1, so we have 4 minus 2 plus 2, yeah, that's 4. Okay, so our point minus 2, 1 satisfies this relation. So we'll say that y is some mystery function of x. We'll then go and take derivatives of both sides. So on the right-hand side, we'll have just the derivative of 4, which is 0. On the left-hand side, we'll have, from our sum rule, the derivative of x squared, which is 2x. Then we'll have the derivative of xy, which will be a product rule. So we'll first have y times the derivative of x, plus x times the derivative of y. And then we have the derivative of 2y cubed. Okay, so derivative of y cubed, we have our function composition. So our outer function is x cubed, our inner function is y. Okay, so from our chain rule, we get our f prime of g times g prime. F prime is 3x squared, so we get 3y squared times our dy by dx. And when we put everything back together, we get that our expression becomes 2x plus y plus x dy by dx plus 6y squared dy by dx. And now we're going to isolate for dy by dx. Okay, so we'll go and move the two terms that don't have a dy by dx over to the right-hand side, and then factor a dy by dx out of both terms on the left. So we get dy by dx times x plus 6y squared, and it's equal to minus 2x minus y. Now what we want to do is just divide both sides by the 6 plus, or the x plus 6y squared. So that tells us that dy by dx is minus 2x minus y all over x plus 6y squared. Now what we want to do is we want to find the slope for the tangent line at minus 2 and 1. So we want to solve dy by dx where x is going to be minus 2 and y is 1. And when we do that, we see that we get 3/4. Okay, so now what we need to do is just use our tangent line expression. So we have the line y minus y0. So in our case, the y0 is going to be 1, and it's equal to our slope times x minus x0. So our x0 is going to be minus 2, and as we said, our slope is going to be 3/4. Okay, and when we put all of this together, we get that our tangent line is going to be y equals 3/4 x plus 5/2. Okay, and then one more example of this. So we're going to find y prime, or dy by dx, at the point pi 1. Again, if we wanted, we could first validate that the point xy equals pi and 1 actually satisfies this curve. We'll just take it as given for the moment that it does. Okay, so the first thing that we'll do is we'll say that, yeah, we have y is some mystery function of x, and then we'll take derivatives of both sides. So on our left-hand side, we have the derivative of x plus the derivative of y squared plus the derivative of y sine of x. So the derivative of x is just 1 from our power rule. The derivative of y squared, we could pretty quickly from our chain rule find to be 2y dy by dx. And then the derivative of y sine of x, we'll get a product rule. So we'll get sine of x times derivative of y plus y times derivative of sine of x. So y cosine of x there. Okay, and then over on the right-hand side, we could pretty easily find from our chain rule, and in fact we already did find the derivative of y cubed, we get that we get a derivative of 3y squared dy by dx. So again, remember kind of I don't know, a simple guideline. Whenever you're taking the derivative of something that has a y in it, you're always going to get a dy by dx, and if you don't, you've done something wrong in there. Okay, so now we get down to, so we've done our derivatives, and we wind up with 1 plus 2y dy by dx plus sine of x dy by dx plus y cosine of x equals 3y squared dy by dx. So we've done all of the hard part, we've done our chain rule, we've done our derivatives and everything. Now what we need to do is just simply solve for dy by dx. So when we do that, we'll put all of the terms that have dy by dx on the left, we'll put the terms that don't have dy by dx on the right. And then we'll factor a dy by dx out of the three terms that are on the left. So we get dy by dx times 2y plus sine of x minus 3y squared equals minus 1 minus y cosine of x. And then we'll go and divide both sides by the 2y plus sine x minus 3y squared. Now what we said is that we want to find the derivative at a particular point. We want to find the derivative dy by dx or y prime at the point x equals pi and y equals 1. So again, we'll go and take our expression for dy by dx and we'll put in x equals pi, y equals 1. Okay, so when we do that, what we see is our numerator is going to be minus 1 times cosine of pi. Cosine of pi is minus 1, so our numerator is going to be minus 1 minus minus 1, so that's 0. And what we see is that our denominator is non-zero. We'd have a sine of pi, which is 0, and then we have a 2 minus 3, so our denominator is minus 1. Our numerator is 0, so that tells us the tangent line at this point is going to be flat. Okay, so that gives us a good overview for implicit derivatives, and there will be a worksheet on this topic sitting in WoW courses, and I will see you all on Monday.